So this I hear a lot is, in one form or another, is you need practice to get the intuition. Practice lets you work out what works and what doesn't. It gives you the estimation skills. You need to practice these things. You can't just delegate it to the computer.
But we're not practicing estimation. I mean, how many times? I mean, I think it's, well, maybe I'm wrong about this now. Maybe there is more estimate. Certainly when I was at school, which was some time ago now, we never practiced it. I never remember ever doing a verbal estimation thing in school, where it said, okay, quickly, tell me, roughly, you know, how many hairs do you think you have on your head? What is the answer to that? I don't know.
Yes.
It's easier the older you get.
Actually, I was asked that just today. I was asked that by my daughter just last night, as it happens, and I told her it was 100,000, because I reckoned it was 1 hair per millimeter in each direction, and her head was about 10 centimeters across, but...
Okay, well, so I mean, but also, how would we estimate this, right?
And I just realized I got the arithmetic wrong when I told her, because that's a million, right? 10 centimeters. No, it's not. It's 100.
But you know, roughly how big are things? I mean, how many people are there in the world? Okay, interesting question. How old is the world? You know, how far are we away from the moon? How are we? You know, I mean, it depends what. There are all sorts of things, but just an estimating actual things. You know, how many people are there in this room? Well, you know, I can count and multiply up. So you know, it seems to me that's something that certainly I never had at school whatsoever, not verbally anyway. And to me, that's something I do every day of the week, all the time. People show me something. People show me, you know, the expense of putting on a conference. And I look at it and I think, is that reasonable? Okay? I don't know. Is it reasonable? I have to look at it and think, well, if I multiply this by this, does it come to roughly that number? Or is it an order of magnitude different? Last night, I was asking people, I want this estimate of how much money we spend around the world on maths education. Okay? In fact, this is a good example of this. And so I got various people to look up numbers of, you know, how much is spent around the world on education. And then somebody sent me a thing saying, actually, STEM only counted for 0.5% of the expenditure in the US on education. And I said, that can't be right. Can't be right. Something's wrong here. Doesn't make sense. Okay?
That's half, right?
No, 0.5%. Right, okay. That was a good catch, yeah. So, but then I looked at it and I discovered they'd left out, you know, teachers' salaries from that. Okay, because teachers' salaries weren't classified as STEM. They were classified as teachers' salaries. So obviously that was nuts. But I mean, you know, I was thinking to myself, well, what was it? Maybe 30% is on STEM as a guess, rough guess, so we can come up with some estimate. But that kind of thing is not hard taught. And I think that's quite discrepant from dragging through hand calculating precise things. It seems
well, I think focusing on estimation there is slightly subversive, because you're skipping out on that there might actually be value in practicing and repeating problem solving using similar procedures, so that you get them very internalized and get an intuition about their behavior and understand their behavior.
Hang on. There was a leap of logic there.
No,
okay,
surely
so
not.
why does, I mean, is it necessarily true that if you just go on grinding around the same thing over and over again, you necessarily get any intuition about it? You might get experience, but you get intuition.
Doesn't experience lead to intuition?
Let me think about that for a moment. Does experience lead to intuition? Not necessarily.
There's a comment.
So no, the transfer is not automatic. Okay, you know, you can have plenty of experiences, zero intuition in the end, just do something extremely stupidly and you will not get more intuition except perhaps about your own stupidity. But look, first of all, a lot of these questions all pertain to the same categories. They're all verbalizations of the same inner fears, okay? And it would have been a good exercise before simply listing them all to see if you can lump them together and realize that there's some underlying fears that are common to a cluster of them at a time. For instance, these are people who are very comfortable with abstraction and not comfortable with what's happening in the real world, to whom we're asking to take time that is already maxed out to assessments and standards that they have to respond to. So all of these things we already know. I've been in these similar conferences for the past 10 years. It's not necessarily about mathematics. You have the same discussions about just about any topic. That's why it's about time to move beyond these topics and look at what drives the behavior of people. You have their emotions that are linked to the goals that they have to respond to, those assessments and standards. So unless we change the assessments and the standards, tweak the system on the edges. You're
Sure.
going to give better tools
Sure.
to solve existing problems, and that in itself is a good thing. Okay, but to go truly beyond that, you're going to have to revamp the system from the top down.
Sure.
I think actually to answer that inner fear, a lot of it comes down to, I learned it that way, I was good at it, it was fine for me. And you take away what I'm good at, so what am I left with?
Let's go up here, because we've got...
I think the problem is that actually, if you look at the way the curriculum and the textbooks and everything that we currently use in the UK, certainly, they spend a lot of time doing the same thing year after year after year, not developing the understanding. If actually schools were brave and said, right, in year 7, we're going to make sure that they do understand some of these things by using, say, computer-based maths, we'd actually find that there was a lot more time in our curriculum.
Yeah.
So that's the first thing. And the second thing about the actual hand calculating procedures. Again, in my revision sessions yesterday, I was working with a boy who had been given a 10-tick style sheet of working out the speed given distance and time. He could do that really, really well, but he couldn't work out time or distance given speed.
Yeah, I mean, he didn't conceptualize the problem. It was just a procedure. That's I think, the key point there. Now, I mean, so let me go on to programming. Because as you know, as I said, and I believe, that the procedurizing that we should be getting people to do is programming. As in, you've got to represent something. I mean, to me, this is just so much more enlightened than hand count. I mean, I think, okay, so let me pull this out a little bit. I mean, we were talking earlier about linguistics, particularly when I'm pleased that, John, I feel slightly better about this morning, the fact that my linguistic example didn't work, and the fact that for some reason there's some weird firewall here that stopped that working, but I guess that's one of these occupational hazards. I should have used my 3G card. It wasn't a screw up completely in what we were doing, which I'm pleased about. But there's linguistics, which so I see this coming from two diametrically opposite sides. There's linguistics, which allows somebody to interface with, in a sense, computational computers without knowing much syntax. So they can get going, get started, get moving without tending to get tripped up. That seems an important thing for sort of moving forward. But at the other extreme, if you really want to actually procedurize something, you need to be precise about it. And in the end, that means writing actual code. I mean, it may be with visual stuff on top of it, or maybe you start with linguistics to get the code. But in the end, you've got to deal with the raw dope. And the raw dope in this case is program code. That's the world. It's the same way as, I don't know, I don't know. In the end, if you want to be a great author, you've got to write actual nice English text if you're English, right? I mean, that's just kind of the raw dope of that. The raw dope is program code. And so it seems to me, and the nice thing about programs is they actually hopefully work. I mean, you can get nice stuff to happen, and quite small programs now produce really nice, colorful, graphical effects. Whereas, the last time I solved an equation by hand, the effect wasn't all that nice. It was a splodge on the page. So it seems to me that this procedurizing thing is really important, but I don't quite understand how to marry the sort of ease of use to get started with taking somebody into the sort of other end of composition. I mean, the programming is like composition in English, basically. It's sort of the other end of that. Comments? Yeah.
I think coming back to the original hand-calculated procedures teach understanding, I think there's certainly a correlation between them, but I think we're mistaking correlation and causation often here. I think certainly hand-calculating can be correlated to understanding, and we see that in the classroom. We see students who practice things and understand them and go on. But equally well, anybody who's ever taught secondary maths can tell you there are students who can pass exams who have no idea what they're doing. They get very good grades at GCSE, you meet them at A-level, and they haven't got a clue what's going on, but they can do the procedures. And so I think we have to be careful not to confuse this correlation and causation issue on these two.
That's a good point.
There's the other type of student as well who can conceptualize things very well, but because they can't do the calculations or make little mistakes in their calculations, they end up getting bad grades and then they feel them down. And so that probably has to be addressed tomorrow in the assessment section. But
yes,
it's
that's
an
an interesting point. In fact, it's almost as a reversal for some of the students. The students who actually, in the outside world might do very well, get put off because in fact and I think often actually a case, certainly that I've observed, is boredom. People get bored. If a certain set of people who are actually quite conceptual get rather bored doing the procedures, they don't happen to be engaged in that. And so they then make mistakes, and they then think they're bad at maths because because they made those mistakes?
Conrad.
Yeah, Deborah.
Okay. Well, in schools in like 4th, 5th grade, they do teach estimation. They take a couple days and they teach it. And then they forget about it, and they never go back to it again. So the students have no idea when to use it, and if they do try to use it, they're penalized because they weren't supposed to try to estimate, even though that's a perfectly reasonable answer to give. Secondly, hand calculations, teaching understanding. Okay, I have a problem, and it's called FOIL.
What's this?
We teach students how to FOIL, so they can multiply binomials. They don't know how to multiply a binomial by a trinomial or two trinomials together because they don't remember the distributive property at all. And that they learn the distributive property at one point, but then it's never followed on, and it's never discussed, it's never even mentioned again, even though they're using it over and over again. So by hand calculation, they need to get their act straight before it's going to actually teach any kind of understanding.
Good. Should we?
So I have just one perspective to add on it. Just I was ranting about long division and how pointless it was with a perfectly intelligent physics PhD. And she was saying, well, you know, I understand division much better for it. And I said, well, explain how long division works then. And when you actually think about it, I don't think many of us, until you stop and think, why does this sort of maximal subtraction of the maximal subdivisor lead to the right answer? And in the end, she conceded the intuition she got from practicing it was to know that it worked. So there was an intuition there, but it wasn't the intuition
How
she
many
thought
people
she
can
had.
actually do long division here? Oh my God, that's a very, very impressive
How
number.
many of you think you could explain why it works? Oh,
Okay,
that's having an intelligent educational
Okay,
crowd.
unfortunately, and how many people have used long division other than in education for the last 10 years? Okay, what? I don't think so.
I did it yesterday to prove that I still could.
A point that's made often to me is, surely the people, you know, who build things like Mathematica need to know the hand calculating things. Even that's false, right? Because the algorithms used to solve things for almost everything that's in something like Mathematica are totally discrepant from what you do by hand. So even if you knew the hand calculating, you know, our developers who build stuff don't, you know, it's totally different. So it doesn't even help on that score. Phil.
So like a pub bore, I'm going to say, stop me if you've heard this before. I've had to miss pretty much the whole afternoon, but I wanted to just to make the point about students making programs as opposed to students submitting procedural assignments. That there's a cognitive dimension to that, but there's also an emotional and affective dimension to that. If the traditional way of working involves students getting validation through submitting to an expert who decides how good or bad their work has been, whereas if you're making a thing, then there is you have a level of validation at the level of whether or not it works, which is a kind of validation which, at least potentially, if it's done right, the student can own. And I think that, again, if it's done right, can potentially make a very big difference to intrinsic forms of motivation. That's something that we can harness.
I'm not
if we
clear
move in
which
that
way
direction.
around you're arguing. You're saying that that's connected with getting a computer to do it with a program or doing it by hand.
I'm saying if you're trying to get a program to work, then that's a project that you can own. That's
I
something
see.
that
Yeah,
you can
I agree
feel
with that.
you can have an investment in, which is over and above. Am I pleasing
Sure, absolutely.
sir or miss?
Yeah,
and
yeah.
and that's got a very different kind of emotional feel. I think it ties in as well to the culture of debugging that exists in computing, where you kind of expect to fail the first time and fold that into your whole procedure. And then you kind of fail, and then you fail better, and then fail better still, and in the end succeed. And that's an approach to mathematics which I find it very hard to inculcate in students if we're working in traditional ways.
When you're coding, when you've got a design problem to solve in code, you always start with a simple way that you understand the problem. And I mean, down the road, you know, after it's been iterated on and you've made it faster, you've made it more efficient, it's nothing like that. But it always starts with what you understand. And that's all I was saying. And so if you're creating, I've never written Mathematica, but I've written things like it. And I wouldn't know how to code up a program that did prime factorization without understanding prime factorization and having done a few. That's my thought.
I think, you know, see, I think this is another, what actually I think is an interesting conversation, and we must go to the questions that we're being non-linear in our discussion here, but that's okay. I think that what you're really saying is, what are the approaches to problem solving something where you don't know what to do? I mean, that's sort of partly what you're saying. Now, I guess you're saying, well, knowing how to do it by hand is an approach. It is an approach.
I agree, it's just one.
It's one approach. I mean, I think there are others, and I think those others, in fact, are important ones to be much more, you know, in the setup. I mean, I mean, like John did with his example, go look up what other people have done. But then you need to have qualification. Do you believe what they've done, or is it nonsense? You know, how do you figure out whether you believe it or not? How is the skepticism injected? Let's go up here. Yeah.
I used to do admissions interviews at Oxford, and we always tested them on curve sketching. And I think if any skill could show the divorce between handheld calculations and understanding, it's that specific skill, because you saw that people were very adept and were very well, and there's no other word for it, drilled to do handheld calculations, and they could solve a differential equation. Then you say, right, what does that solution look like? And not a clue. A function would be there, but no understanding of what a function was. So I think it is really a myth that handheld calculations are anything often more than a mechanical process.
Mm-hmm. There was a comment in front.
And then perhaps we should move on.
Yeah.
I just want to put a different perspective on the hand calculating and understanding issue. We had an example this morning from Terry, an autograph slide of a student who'd investigated the locus of minima, was it, of cubics, and found that they all fitted on a quadratic curve. I wanted to ask, did that student prove that that result was true? How did they do that? Well, they could have used the computer algebra system, couldn't they, to have done a bit of algebra. My feeling about that problem is that I would have wanted to do some hand calculating to get an understanding of what was going on there, that I could have used the graphical work to get a conjecture, used the computer algebra system to prove it, and not have had a clue about what was really going on. Was proving on your list of 10 things?
Okay, so proving is an interesting topic.
Which I was going to put under, it isn't maths. It's on my list right here. It teaches you nothing about proof.
Gosh, proof is a big ball of wax, because it's so here's something which most people who are mathematicians here will hate me for, but I have to say that the tradition, so proof as a way to understand logical thought, I think, is kind of very important. And it doesn't matter whether it's with a computer or not. And I have to say, it's not proof, but a lot of stuff you do in programming is connected with that. I think it's a similar line of thinking, though it's not proof, okay? When you talk about what's done in the real world with, a new mathematical theorem got proved, I find this really quite dicey. I mean, the fact is, what that means is 10 people in the world agreed that something was right and tried to check the logic of it. That's one kind of proof. Did they get it right or wrong? So it goes both ways, frankly.
What you mean is they can't disprove it?
Well, yes, at that moment they can't disprove it. But that's not, I mean, in science, that's a very understood concept. Something is okay until, at least since Einstein and things, when people got used to the idea that everything could be wrong, including in this very room. But I think in maths, there's an idea you can prove something, and that's a standard part of maths. And indeed, of course, there's a great, that's a very major part of maths. The issue I always have with proof is I think that people think that's a much more solid, practical form of proof than what I would say was, let's say, heuristic proof, where you get a computer to run tests, billions of times to check things, lots of times. Or, you write a piece of software and people are pounding on it in all sorts of different ways, and you see whether it has a bug or doesn't have a bug. In practical terms, in the modern world, that kind of proof, if you want to call it that, though most mathematicians wouldn't, that kind of proof actually guarantees fewer errors than the traditional sort of proof. So in terms of what do we do in education, it does seem to me like the idea, the concept of logically following through steps to show that something must be true is really important. I don't quite know how that fits in the whole computer-based thing.
I want to give a different perspective, actually, because I see this slightly differently. I look at mathematical argument and counter-argument as being a continuous spectrum. Sometimes you do very fuzzy things like the sales guys will make a projection what sales will be next month. And they make an argument for why I should believe it, and I make an argument for why it's bogus. And proof is one extreme case at the very end of that. But what we're not doing is we don't teach any of the intermediate. We don't have people present models like my projectile thing and have other people say, but surely you've ignored the too big a thing here. So that's where I'd like to see all the work, rather than, they can specialize in the super argued version that proof is at a later point in education, but they're not understanding skepticism and attack and trying to hack where goes wrong with the model.
One question I don't understand, how do we inject skepticism? Right? I mean, because that is, it's like, I always like, one of our modules starts with the thing, I would love us to find a YouTube clip of some government minister saying, the following is true, okay, some piece of statistics, and it's just complete nonsense, okay? And you can tell, anybody who's really can connect the dots can see this does not make any sense, okay? It can't make any sense. But we don't inject people, most people, our mathematical education, most people doesn't inject that kind of skepticism at the moment. And I don't quite know how we achieve that skepticism.
There's some questions over here. Perhaps we could take third row first.
Saying that, proof, formal mathematical proof, is no different from heuristic proof is to misunderstand what a mathematical proof is about. And I think there is one of the things which I'm most excited about computer-based maths is how good this is for proof and how good this is for pure mathematics. As you say, it's difficult because a lot of pure mathematicians don't see this because it's not their background. But the simple truth is that within pure mathematics, there are discussions about proofs which have been done computationally.
Absolutely, yeah.
And this has come in quite recently to a number of different problems. And those proofs are no more or less valid, in my opinion, than other mathematical proofs. A set of calculations is not a proof. And there are some very good examples of this, of unknown problems, where people have calculated to however many digits, but they still don't know. We still don't know whether they're right or not. And this is about knowledge.
Let's take a few more, Phil.
I think the statement that proof and calculation are not the same is very important. And that confusion between proof and calculation is out there in the culture. I think it's out there in the culture of our students, certainly. And I think back to my first job, which was actually as a school teacher a long time ago, teaching GCSEs back when we did things called investigations. And you would ask at the end, if you were an assiduous teacher, for some sort of answer to a why question, some sort of proof-like argument at the end. And almost always that would be interpreted, and I don't know where the kids got this from, I don't know what part of the culture it came from, I didn't tell them it, that what I meant was do some algebraic manipulation at the end, whether or not that was appropriate. We need to somehow get the message across that proof and calculation are separate, and if we automate one, we don't obviate the other.
Yes, thanks, Phil.
I just want to get back to the skepticism part. I think that as teachers, we need to model that if the students aren't doing it themselves. And what you can do is, just have the students put up their results, and I usually ask the class, well, do you think that's correct, or does that make sense? And if they're not responding, well, I might say, well, that doesn't make sense to me. So I think it doesn't have to be quite as complicated as going through epistemology and all this. There's very simple things that we can do to make the kids more skeptical, but I think we need to model that as teachers so they can see how's that done, and then it transfers to the students, I think, as well. And
in fact, some of the modalities we flashed up earlier were an attempt to bring that kind of critiquing into the standard what should be part of computer-based math. I think what we should do is take a couple more comments, and then we probably shouldn't go any further. I think we're all going to run out of steam otherwise completely. Let's take a couple more comments, one up here and 1, 3, and then 1, 2, 3, linearly or non-linearly.
Two thoughts. One is that I think nothing kills skepticism more than hand calculating in our current textbook system. I love the quote by Sir Ken Robinson that he says, "We teach students that there's one right answer, and it's in the back of the book, and don't look." And that's the approach to math that we teach. And so, of course, there's no skepticism. They look at the back of the book, they get feedback on whether they're right or wrong, and that's the end of the day. And then I also had a question. The feedback I get when I try to tout this philosophy is that if we do computer-based math entirely, we will no longer have like good old-fashioned mathematicians or programmers. So I hear from our BC Calc teacher, you know, we need to teach this stuff because who do you think programs your calculator and who do you think programs Mathematica? So how can I best respond to that? Can we still produce mathematicians, pure mathematicians, even in a setting where we're just using computers, or is that too idealistic?
That's an interesting question. Let's hear the other two, and then we'll try and do that to round off the session.
So just a story from my undergrad. The professors at my university get quite a lot of really crap proofs sent their way of various things. And this one person had proven that there was a quintic formula in 75 pages of algebra. And we were expected to go through and debunk and figure out where the error was. And I think to myself now, I wish to God we had Mathematica, because it would have been a lot easier to do all these substitutions, et cetera, and find the flaw in the apparent proof this person had constructed. So I think that in some cases you can use these programs to find the bugs, to find the errors in computation that humans can't do very, very easily.
Mm-hmm. And there was one more just here.
A lot of the computer-based math that I will teach would be how to use statistical tools the right way, how to test something to see if it's skeptical. And for there, you can use very high-level functions, like, well, you know, like solve or do some simulations or some Monte Carlos or that sort of thing. But the people I'm teaching, and for me for that matter, I'm not going to go out and develop, sort of a fancy new way of estimating time series, econometrics, you know, because that's a very different set of skills. Right? So the people who actually develop the new techniques, you know, have to learn different stuff than what you have to do to use the techniques.
I agree. So let me perhaps round out with a further comment on that, which I think that's a very good question. Look, it comes back to my driving versus being an automotive engineer or mechanic. Now, you know, does it mean that if you teach people, if the mainstream subject is driving, does it mean that nobody ever becomes an automotive engineer? No, it doesn't. I think that's perfectly, you know, it's a perfectly valid thing. I think, in fact, in the case of maths, the automotive engineering piece is changing. I mean, it's to do much more with how do you program the computers to do these things? How do you make new algorithms that will do things better at that high level? Okay. But there are certain skills that are, I guess, equivalent to sharpening quills. I mean, you know, we used to all write hundreds of years ago with quills, and we don't. And, you know, I don't think there are many quill sharpening specialists in the world anymore. That's just the way life moves on. There are some skills that get lost. And so I think there may be certain mathematical skills in that category as we move forward. But, you know, in the end, it seems to me, you know, the great advantage of sort of, you know, being on top of automation is that you can do, the scope of what you can do is so much greater. It's true that you lose, as with all progress, one tends to lose certain things on the way. The question is one gain more than one loses, and can one minimize the losses? You know, I think that's sort of the way one should view it. Just like people say to me, well, you know, isn't it nice if people get the beauty of learning how to hand calculate this other? Perhaps. And the ones who want to do that can go off and do that. That's great. It's a good thing. If they enjoy doing that, fantastic. There's nothing better than getting something you really enjoy. But, you know, you get so much more scope, which will engage so many more people, I think, if you do the thing that's on top of the automation and that gives you that greater scope. So I think that's the way I would think about it.
I think for me, it's a pure numbers game. We're teaching, 500 million people maths around the world? And if you look at the number of people who use maths in their lives in a serious way, maybe that comes down to 100 million or less. How many people do we need programming math systems like Mathematica? Well, we make do on a few hundreds. Maybe it's 10,000 worldwide. So it's a narrow part of it. The mainstream subject is that 100 million who might use maths.
But people can self-discover these things. I mean, it's not like, you know, we have to assume that we didn't teach it, and therefore they didn't go off and enjoy doing stuff. That's one of the great things in the modern world. You can go find stuff all over the place, all over the web, to help, you know, to encourage interests that you have. So I don't think it blocks out the kind of Olympiad maths crowd or anything like that. Good. I think we should round out. That's been a great session, and you know, let's thanks to everyone.